In the last lesson, we had started with this problem. Let us remind ourselves what it's all about, because we need to finish it. We had the laser light of wavelength 500 nanometers is incident normally on a diffraction grating. The resulting diffraction pattern has diffraction maxima up to and including the fourth order maximum. Calculate for the diffraction grating the minimum possible line spacing. So we found that this line spacing, that means the distance between two consecutive lines, was 2 times 10 to the power of minus 6. And remember that with these conditions, under these conditions, we could see up to the fourth order maximum, the fourth order bright fringe, in other words, not beyond that. And we applied this information, but now in the next question that we stopped, it says the light in B, this light now, which was 500 nanometers, is now replaced with red light. State and explain whether this is likely to result in the formation of a fifth order diffraction maximum. Now, in order for us, you know, when we do diffraction gratings or double slit experiments and so on, we need to remind ourselves about the beginning and the end of, in terms of wavelengths of the visible spectrum. The one end is the red end, the other end is the bluish violet. And we need to remember which has the biggest wavelength or the smallest frequency. And here is the spectrum, the visible spectrum, to remind us. Look at this. This is supposed to be the blue end. Usually we call it the blue end, but although it's violet towards the end. And this is the red end. You see, roughly the visible spectrum is from about 400 nanometers, these are nanometers here, nanometers, from about 400 to 700 nanometers. So you see the red has the biggest wavelength from the visible light. So whatever wavelengths are close to the red, whatever colors are close to the red have the biggest wavelength. So now, in our problem, we had a light which was 500 nanometers, and now we replace it with red, which is 700 nanometers, which means a bigger wavelength. Now, where are we? 1621. Here we are. Yeah. So we replace it with red light, which has it has a bigger wavelength than the 500 nanometers. Let's say here 700 to remind us. So the wavelength of red light is longer than this greenish color that we had before. State and explain whether this is likely to result in the formation of a fifth order diffraction maximum. In other words, okay, here we see 4 maxima, 4 orders, I think, fourth order. Here's the first order where n equals to 1. I don't know how to get rid of this block anyway. Here would be the second order, the third, and some of the, I don't know, the fourth. We could see up to the fourth with this color. Now, are we going to see any more up to the fifth, for example? Well, you see, let us see again this picture. You see, when we have a big wavelength, when we use light of big wavelength, the interference pattern that we see on the screen is quite broadly spaced. And as you can see here, we have a blue color and a red color, like, I mean, it's illustrated in the picture. And here, of course, will be the central maximum. You see, the blue light forms a pattern which is more narrow. I mean, if this is the first order for blue light, look where the first order of the red light is. That would be for the blue, and this would be the first order for the red. you see, it is further away. When we use, the bigger the wavelength of light that we use, the more spread out the pattern. And why? Because you remember what is generally this formula that gives us the condition of where we have maxima. In other words, bright fringes from the interference of light going through a grating or a double slit. Isn't it d sine theta, sine theta equals to m lambda, or I think in your book this is called, this is n they used. Oh, come on, n here. Okay, let's leave it n. Where n is gives us the order of the maxima of the bright fringes. You see, the bigger the wavelength, the bigger this angle theta or the sine theta. So that is why when we use red light, which has the biggest wavelength, 700 nanometers, obviously this is the biggest angle theta here. I mean, the angle that gives us the first order maximum is bigger than the angle that gives us the first order maximum for blue. And which means now, if we go back to our exam, the question is that since we use now a bigger wavelength, the pattern here on the screen that we're going to see is spreads out more. So there's not a chance that we are going to see a fifth order diffraction maximum, as they call it. Fifth order diffraction maximum. We're not going to see that. If we were using a smaller wavelength, smaller than 500 nanometers, perhaps, well, calculate it. But now we can't. We are not going to see fifth order because our pattern will spread even more on the screen. It will become a lot broader than what it was with the 500 nanometers light. So if you have any questions here, guys, please send me a message. Yeah? Okay, so what, that's it, that's the answer here. So the answer is no, we're not going to, because the wavelength of the red light is bigger than the 500 nanometers that we were given, which means this will be bigger for the red light. The angle will increase, becomes bigger, which means that the pattern becomes broad, on the screen, spreads out, whatever, becomes broad or spreads out, whatever you prefer, spreads out. And we're going to see, we will not see, I will not see fifth order maximum. Okay. I hope you agree with his answer, because be careful with whenever you have this type of problems with gratings or double slits and so on, they will always ask you this question: what happens if we change the wavelength? And you need to know how to find the answer. And remember, you can always trust this formula. And hey, my pen doesn't always write. So if you see it in this way, you know, when you increase the wavelength lambda, you increase this angle theta and the sine theta. The angle theta increases and the pattern on the screen spreads out more, becomes broader, and vice versa, of course. A similar question, instead of changing the wavelength, they could tell you that we change the separation of the slits. What happens? And again, we are going to think in terms of this formula. I mean, say, for example, that we decrease the slit, the slit separation, the separation between two consecutive lines on the grating, or we decrease the separation of two slits if we have a double slit. what happens there? We can solve for sine theta here. Look at this. Sine theta equals n lambda divided by d. If the slit becomes smaller, if we decrease it, look at this, because the d is inversely proportional to the angle. The bigger the slit, the smaller the angle. It means the narrower the pattern. And the larger the slit, the slit separation, the smaller the angle. What did I say now? They're inversely proportional. The smaller the slit, the larger the angle. The bigger the slit, the smaller the angle, the narrower the pattern. So it's the way to find it. So it's not really difficult. Okay, so we had enough with this problem. Let's look at another past exam paper, because they love the double slits. And what is this? From 2018. 2018, this one. Let's see this one. Question 4. Okay, let's make it a little bit bigger. You can see already we have a double slit there. All right. Okay, state the principle of superposition. There's always some definition, isn't it? Okay, what do we say about the superposition? Superposition is when two, sorry, when two waves pass through the same area in the medium and overlap. And when they overlap, their displacements add. So what do we say here? When two waves overlap, when two waves overlap, their displacements add while they overlap. Their displacements add while they overlap, of course. And the resultant displacement, of course, is the sum of the two. Okay, the algebraic sum. All right, so we know what to do there. Now let us go to this problem. An arrangement for demonstrating the interference of light is shown in figure 4.1. Okay, so light of wavelength 610 nanometers falls on these two slits. The wavelength, okay, the wavelength of the light is 610 nanometers. The distance between the double slit and the screen is 2.7 meters. So between here and there is here it is 2.7 meters, all right. An interference pattern of bright fringes and dark fringes is observed on the screen. The centers of the bright fringes are labeled B. So wherever we have a B is a bright, it's a maximum. And the centers of the dark fringes are labeled D. All right. Point P, there's point P. Point P is the center of a particular dark fringe, and point Q is the center of a particular bright fringe, as shown in the picture. Okay, here's the P and the Q. The distance across 5 bright fringes is 22 millimeters. They show it to us. It's between the distance across 5 maxima, in other words, is 22 millimeters. Okay. So look at this. They give us this distance, and they give us distances between fringes, between maxima, and they give us this distance between the two slits. Obviously, here we are going to apply this formula, lambda equals AX over D, which is mentioned in the curriculum. Anyway, so the light waves leaving the two slits are coherent, obviously. State what is meant by coherent. Okay. State what is meant by coherent. It's one mark. It's another definition again. What they want you to say is that there is the two sources of waves emit waves which have a constant phase difference. So they want to see the constant phase difference. But in truth, I should say that they are in phase, that the two waves are in phase. It's not enough to say constant phase difference. Anyway, so this is what they want. So the coherent are two sources when they emit waves which have, they have a constant phase difference from one another. But in particular, in this type of experiments, in the double slits and gratings and so on, the two waves must be in phase, exactly in phase. So, because they might have a constant phase difference, but how about if they continuously have a wavelength phase difference, and we wouldn't have a maximum in the center of the screen, for example. Anyway, so they want you to say that the two sources of waves have a constant phase difference. So it's in terms of phase difference. Okay. Now, oh dear, we have to go to the next page, but we need a diagram. Now, state the phase difference between the waves meeting at Q. Now, let us see the diagram again. Look at this. Here's the Q. And they told us that whatever is point B, these are maxima. This is maximum, and this is also a maximum. And let's see what order maximum. And this is the one in the center, opposite the screen. So this would correspond to n equals 0. And this would correspond to n equals 1, and then the next one, the second order maximum. Sorry. Okay. All right. So what do we need to say now? What is the phase difference? What is what? State the phase difference between the waves meeting at Q. Okay. So here is the Q. The Q, as we can see, the Q is a maximum, which means that whatever waves meet there, they are in phase, isn't it? So the phase difference, because it is a maximum, we can say that the phase difference, if we are to express it in terms of an angle, could be 360 degrees, or we can even say 0 degrees, because they will differ by one full wavelength. All right. The next, so here our answer here, the phase difference is 360 degrees or 0 degrees. Oh, here's the degrees. All right. Calculate the path difference in nanometers of the waves meeting at P. So calculate the path difference of the waves meeting at P. Now at P, look at this, it's between two maxima. This is a minimum now, okay? It means it's dark, the middle of a dark fringe. And since it is a minimum, means that whatever waves meet there, they are out of phase by exactly 180 degrees, isn't it? But in terms of nanometers now, in terms of wavelengths, let us see. Waves that meet here at the center are exactly, they differ by 0 degrees, okay? Now this is the first maximum, the first order maximum, which means waves that meet there are out, differ, but they pass different by a full wavelength, like lambda, by 1 lambda, in fact, because it's the first order. And here, since it's the first minimum after the first order maximum, obviously here, whatever two waves meeting there would be out of, their paths would differ by 1.5 wavelengths, isn't it? So here the difference would be 1.5 wavelengths, the difference of paths between two waves that meet at point P. So one wave that comes from there and another one that comes from the other slit would differ by 1.5 wavelengths. So if we are to, we know this wavelength because it's given, 610 nanometers. So remember 610 nanometers. So the path difference between two waves traveling from each slit will be equal to 1,5 lambda, which is 1,5. The lambda is 610 nanometers. Nanometers, and this gives what 920 nanometers. So this answer here is 920 nanometers. This is the path difference between two waves, one from each slit. If these are the two slits, and here is the point, what is this point P? That means the one wave that travels this path and the other wave that travels this path are out by this distance here, which is 1,5 lambda. And this is equal to 920 nanometers. I hope you understand what it means. Eh? This is the path difference. Okay. Now, determine the distance A between the two slits. Okay, determine the distance A between the two slits. Now, remember the formula that relates the distance between the two slits and the distance of the double slit from the screen, which is called D. This is the D, and it's given is 2,7 meters. And what else? The X in this formula is the distance between two consecutive fringes, bright fringes, maximum. Okay. Here we are given the distance between 5 maxima to be 22 millimeters. Therefore, we can find the distance between two consecutive fringes, bright fringes, isn't it? So let's start again with this formula, which is lambda equals AX divided by D. We say. Okay, so remember that X is the distance between two bright fringes, two consecutive bright fringes. Okay, so in our case, we are given the 22. What is this called? 22 millimeters is the distance between 5 fringes. Millimeters is the distance between 5 fringes. So the distance of 2 fringes only, so the distance X that we want is actually 22 millimeters divided by 4, isn't it? Because look at this. From B to B to B, we have 1, 2, 3, 4 spaces, isn't it? So this 22 millimeters, we have to divide it by 4 to find the distance between two consecutive two consecutive maxima. So there we found the X. What is this now? This is 5,5 millimeters. So this is our X that we need to use in this formula. So what do we need to find now? We need to find the distance, this A here, we need to find. So if we solve for A here, the distance between the two slits, this is lambda times D divided by X. And the lambda, which is 610 nanometers, 610 nanometers. So let's make it, change it into meters by multiply by 10 to the power of minus 9 times D, which is the distance between the double slits and the screen, which is this distance, which is 2,7 meters. So this is 2,7 meters, the D, and the X, there it is, 5,5, but these are millimeters, times 10 to the power of minus 3 to make them meters. And, what is this now? Okay, apparently this is 3, 0 times 10 to the power of minus 4. So our answer is that the distance between the two slits is 3 times 10 to the power of minus 4 meters. Okay. So this is this formula, be careful. This is one of the two formulas that you need to know when you do this type of calculation with double slits and gratings. The other, remember the other formula, the very important formula for the double slits or gratings is the one that relates the angle formed by the various maxima with a wavelength and the distance between the slits, whether it is a grating or double slit. In fact, although this is given as applied to gratings, it also applies to double slits. Okay, so this is the one formula that you need to know, and the other is this one that links the wavelength with a geometric kind of arrangement of the apparatus. Whereas this one, if you notice, it's not so much, does not link actually with any apparatus. It just links the wavelength with the distances between the slits. And the sine theta gives you simply how broad the pattern is on the screen. So you see, it does not depend on how far the screen is or how near the screen is from the double slit or whatever slits we have. All right, now, so here is the distance between the slits. We found it. Now, a higher frequency, of course, will give us now some other type of light. A higher frequency of visible light is now used. So remember, the light that we used up to now was 610 nanometers. Now we have a higher frequency. Higher frequency means lower wavelength, smaller wavelength. A higher frequency of visible light is now used. State and explain the change to the separation of the fringes. Okay, so higher frequency means smaller wavelength. Frequency and wavelength go opposite, isn't it? So higher frequency, if the frequency is higher, means that the wavelength is smaller, shorter. So smaller wavelength, that's 610. And if the wavelength is smaller, obviously the pattern is less spread or narrower. So, well, narrow, we can say narrower pattern. Or a smaller spread on the screen, which means the separation decreases because they want the separation of the fringes on the screen. The separation decreases. Obviously, since the pattern will be narrower, isn't it? The fringes will be closer to one another. So their separation decreases. And if we see here the fringes, here is one separation between two maxima from B to B. The separation will decrease if we use a smaller wavelength. What is this smaller wavelength? Yeah. Okay. I hope this makes sense, people. You need to understand this very well. You need to be careful. You need to play with these values of bigger and smaller wavelengths or frequencies and know what to do with them, okay? Now, the intensity of the light incident on the double slit is now increased without altering its frequency. So in this case now, we don't change no frequency, no wavelength, but we change the intensity. More intense light is falling on the double slit, but the same color. compare the appearance of the fringes after this change with their appearance before this change. So what difference we are going to see on the screen if we use more intense light but of the same color, same frequency of wavelength? Well, if we don't change the color, I mean, look at the, remember this formula? We do not change the color. This is still the same. This is still the same. The angle will be still the same, which means the separation of the fringes will stay the same. There's the position, the maximum, the position of the maximum will be the same. So there is no change in the position of the maximum or in the separation, no change in position of maxima. So all the bright fringes will appear where they used to be. Okay. Then what else? Now, but now the maxima, since we send more intense light, the maxima will be brighter. I mean, makes sense, isn't it? The maxima or the bright fringes, the maxima will be brighter. Will be brighter with a more intense light. What else can we? Obviously, there will be no difference in the dark fringes, isn't it? The minima, in other words, the minima or the dark fringes will not change. I mean, what change can you see in the darkness, isn't it? It will not be affected. So there will be no change here. Only the maxima will be brighter, and that's it. That's all that we can say. Okay, the dark fringes will not change. The bright fringes will become brighter, and all the fringes will be where they used to be, in the same position.